Hello everyone, my name is Alistair Bihari, and my presentation today is on lightweight dependent types for scientific computing. I'm going to be showing how we can use F# to create a more advanced type system for working with things like vectors, matrices, arrays, tensors, and other structures that we encounter in scientific programming, and why functional programming, and F# in particular, is a great language for doing scientific computing. So, about me, my name's Alistair. I'm from Trinidad and Tobago. That's in the West Indies. That's in the Western Hemisphere between North and South America. Indians from the Indian subcontinent came to the West Indies and to Trinidad in the 19th century as indentured laborers under British colonialism. Today, Trinidad is a multi-ethnic and multicultural country. We have a lot of different religious festivals and customs and things like that everyone celebrates. And of course, you probably also know us from cricket, which is very, very popular in India and in the West Indies as well. So the project that I'm currently working on right now, it's called Sylvester. Sylvester is an F# domain-specific language for scientific computing that focuses on things like safety, expressiveness, and interoperability. And the idea is to take the best parts of type functional programming. F# is a type functional language, and apply these things to scientific and mathematical computing. And well, we will see how we can use some of F# features to create a type system called lightweight or restricted dependent typing that we can use when we are doing scientific computing. So what makes functional programming so good for scientific computing? Well, right now today, scientific programming, it's dominated by languages like C and C++, by Fortran, Java, Python, R, and languages like these. And the older languages, they tend like Fortran, or well, say like C++, they're statically typed. Fortran is procedural. The newer languages, they are dynamically typed, like Python and Julia, and they also have object-oriented features. But they are all mainly imperative languages, and they all mainly depend on mutable states and variables. And also, languages like Python and Julia tend to rely on metaprogramming. So if you think about TensorFlow, what you're doing is you're basically building a graph, but the actual computations are actually executed by lower level libraries. So that's an example of meta programming. So some of the language strengths of F#, well, of course, it's a functional language. It's expression based. Functions are first class citizens. You have immutable variables and pattern matching. But F# also is also a multi-paradigm language. So it's functional and object-oriented. You have object-oriented features like classes and interfaces, inheritance, and things like that. You can choose to use immutable variables when you need to. And also, you can choose to use dynamic types using the .NET Dynamic Language Runtime. And actually, we'll see how we can use the DLR in our data frame data structure. And one thing about F# is that it has very powerful metaprogramming capabilities using type providers and computation expressions. And it can interoperate, well, any language that has a CFFI, like TensorFlow and Torch, or things like that. It can interoperate with F# very easily. So all of these things make F# a really great language for doing the same sort of things that Python and Julia and R do today. Okay, so I can just give a short example of Sylvester syntax. So here we're doing some basic exploratory data analysis. Typically you would use, if you're using Python, you'd be using the pandas data frame, but in this case we're actually using, we're going to be using Sylvester, and we have a data frame structure that we can use. So we can see that we can basically use dynamic types when we're using this data frame structure to make the actual syntax very easy. And we can also use things like link when we are doing queries. So actually the properties that have a question mark, these are actually dynamic properties that actually come from the data. But the methods that have the traditional dot syntax, those are statically typed. These are statically typed methods and members. So what we can do is we can have a mix of dynamic and static typing when we're working with data. So we can do the same things that you can do with Python and R using pandas. You can do with F# and Sylvester, even though F# is a statically typed language. Okay, so I can just run this. This is Visual Studio Code. This is a great open source IDE for doing F#. Okay, so we're just basically calculating some statistics on the data. Okay, so another thing about F# is that there are a lot of different open source environments you can use. Right now I'm using, this is Jupyter Notebook using the IF# kernel. So F# can run both in Jupyter Notebooks and also in IDEs like Visual Studio Code. And this is really one of the great strengths of F#. It's built on .NET, which has been around for a very long time. It's supported by Microsoft. You have great open source tooling environments, Visual Studio Code, Jupyter, and you also have a really great open source community to rely on. Plus, in addition to that, you also have Microsoft, which is fully committed to open source .NET and regularly puts out really great libraries like ML.NET. So F# is actually a very it's a very good language, and thinking of learning and adopting for doing scientific computing. So the main thing I want to talk about is how we can use F# to create this type system for doing scientific programming. So just give a short example. So in this code snippet, I'm creating a vector of length 1000 and I have another vector 500. Now if we do an element, if we try to do an element-wise addition, this will actually fail because the two vectors are of actually different lengths. Now typically if we were using Python or Julia or really any one of the traditional languages for doing this type of programming, this type of error would only actually be caught at runtime. But actually in F#, and this is actual F# code that's running inside the Jupyter Notebook, what happens is that the code actually does not compile. You get a type error because the lengths of the two vectors are not the same. Okay, and so this is basically an example of what we call lightweight dependent types. Okay, so the basic idea of dependent, the simple explanation is that the types simply depend on values. So for instance, you can have a vector, just as we saw, that depends on the length. So the length of the vector is actually encoded in the type. And what it lets you do is it lets you, gives you more advanced program verification than just ordinary type checking. And as we saw, a lot of type errors can actually be caught before the program actually gets to runtime. So if you're doing scientific computing and you need to have like the safety built in, you can actually use dependent types to make sure that things like those sorts of errors, like out of bound errors, are actually caught at compiled. So let's look at some F# code using Sylvester. So on this line, I'm creating an ordinary F# array. And you can see it has basically it has 1,000 elements. Now, if I try to index this array outside of the range, the code is going to compile, but what's going to happen is it's going to throw an error at runtime. So when I execute this, so you see here, okay, it says it throws an index out of range exception because the bounds were actually exceeded, but this code only happens at runtime. Now here's a different way of creating it. This time I'm going to be using a Sylvester V array. So I create an array, it has 1,000 elements, but as you can see, the type annotations actually are saying that the type of it, 1,000 element, the type actually contains the length encoded as part of the type. Now what this lets us do is, so if I try to index this array, let's say I take the fifth element, then that's fine. But suppose I try to go outside the bounds of array. Well, what's going to happen is that the type checker is actually going to throw an error. And the type checker is going to say, okay, well, this actually, you're trying to index this out of the bounds of the array. But the important thing is that this actually happens at compile time. The F# type checker is actually getting this error. So before we actually get to runtime, we can actually catch this error. And of course, if I change the index of the array, something like, okay, well, 999, well, okay, now it's okay. So now it actually, you see the error message goes away. So this actually is a valid expression. If I go outside, so again, the type checker actually tells me that this expression is actually not valid. Okay, so this is an example of, this is basically just a basic example of what's called lightweight dependent types. So we have full spectrum dependent types. These types basically, they can depend on most of the runtime values, and all of the popular dependently typed programming languages like Idris, Agda, ATS, or F star. This is the kind of dependent types that they use. And if you're programming these languages, you have to write proof carrying code that can verify that basically these their values and actual types, well, they're basically that they're compiled, that the expression actually makes sense, that it satisfies whatever constraints that you're using. But so, I mean, this idea of dependent type is actually very cool. And a lot of things like safety, it's a very good mechanism for enforcing safety constraints. And of course, languages like Idris, they have been actually getting some more attention in recent times. But the only problem is that right now, dependently typed programming languages, they're still a niche area. They have a small user community. And also, there isn't that, I mean, compared to languages like, well, compared to C#, to F#, there isn't that big of a community with, tooling and libraries and things like that. So finally, we come to this concept called lightweight dependent typing. And basically, the idea is to bring the safety benefits of dependent typing. So as we saw, having arrays where you can actually do bounds checking at compile time, bringing them to more mainstream languages like F#. And this was actually pioneered by dependent ML, which is actually a precursor to the language ATS. But we can use these techniques in languages like F#. We can implement this idea of lightweight dependent typing. Okay, so, and we're just trying to extend the type system a little bit that allows us to basically to capture these properties at compile time, these safety properties at compile time. The restriction is, and this is what makes basically lightweight dependent typing different to full spectrum dependent typing, is that the actual values, they have to be statically known before the expression is evaluated. So you aren't allowed to use just any arbitrary runtime value. The value has to be statically known, which typically isn't that big of a problem in scientific computing. Usually it's more of a closed environment where basically you have these static numbers that are known upfront. So what Sylvester does, it implements this idea of lightweight dependent typing for arrays, basically these collection types, vectors, matrices, and tensors. And what it does is it lets you have this type level arithmetic on the actual natural number dimensions. So basically arrays, vectors, matrices, tensors, they all use natural numbers as their length of their dimensions. And if we can implement this type level arithmetic on these dimensions, we'll be able to write functions that actually have constraints. So we can constrain our functions to only accept, for instance, only matrices of a certain dimension, or only square matrices, or vectors of a certain length, and things like that. So one question is, well, what's the difference between lightweight dependent typing and type level programming? Well, of course, languages like C++ and D and other languages, they support type level arithmetic, where you can have static values as template parameters, and you can actually do checks at compile time to actually verify that that indices are in within range, or the dimensions of matrices, they actually match up. But like to dependent typing, it goes beyond static typing, because you have the types. I mean, the types, they do act as true dependent types, where they're actually varying on the values, and we aren't actually relying on compiler, any sort of compiler certs, or static ifs. The actual types that we generate, they're parts of whatever problem domain that we are in, and so it's actually, so basically, lightweight dependent types, they're not simply just types, not type level arithmetic, but they're not full spectrum dependent types. They actually fall in the middle between the two. Okay, so I can give an example just of how Sylvester does some of this. So here we see we have, so we're declaring two variables, and these are actually just type instances of natural numbers. And you can see here that the condition that a is less than b, this actually gives us it's not it's not an ordinary Boolean value. It actually has basically, it's actually a different type. So if I do the reverse comparison, so the type actually changes. So this is not so typically in typical F sharp, of course, whether when you do a comparison, the type stays the same. But in Sylvester, these sorts of comparisons actually result in different types. And the same thing holds, for example, for equality. Okay, so we know that, well, of course, a is not equal to b, so the type of this is it's Boolean true, and the idea that a itself is equal to b, well, of course that's false, because a is not actually equal to b. And we can actually write these check constraints. So what we can do is we can have in our function, we can have check constraints that tell us that, okay, if it is that the variables don't satisfy some constraint, then the type check will actually fail, and the code isn't actually going to compile. So this is how at compile time we can implement these sorts of checks in our data structures like arrays and tensors and things like that, that can actually detect when the dimensions don't match or arrays are out of bounds. So really using this sort of dependently typed natural number arithmetic. And again, what happens is that we're not using any sort of compiler assertions that will just cause the compiler to stop. So for instance, if there is an underflow, if we try to go, for instance, less than 0, what we get is actually a type. It's not a compiler error, it's actually a type. Okay, so that type is actually enter an underflow. And so we can actually check to see that the type isn't actually equivalent to that. But we're not doing anything that causes the compiler to stop working. We're still actually inside the compiler, inside the environment. Okay, so we can look at some dependently typed linear algebra structures. Okay, so here we have, so let's start off with some vectors. So again, we're declaring two vectors of length 100 and 200. So you can see that we're using the numeric length as a parameter. And you can also see these are just type annotations that the IDE puts, but you can see that the length of the vector is actually part of the type. Okay, and so I can get the length of the vector, which is a type natural number. So we see here the length of it is actually 200, and well, we can just declare another variable. So now, if I try to do an element-wise addition, so we have two vectors that are length 200. If I try to do element-wise addition, then okay, that's fine. The type checker doesn't complain. But if I try to do element-wise addition of two vectors that aren't the same length, then the type checker complains. The type checker wants the two vectors to be of the same length. So of course, so this code actually would not compile. Whereas if you're using a language like Python, of course, the code will actually run. The error would only happen at runtime. Assuming you do actually get an error, not just have something being like incorrect, without causing the program to stop. So in this case, this operation here, we're doing basically we're doing a scalar product. So we have a scalar product of two vectors, and that gives us a scalar, so that's fine. Also, we can of course do multiply a vector by a scalar. But if I try to take the scalar product, the scalar dot product of two differently sized vectors, well, again, it gives us a type error because this operation isn't defined for any vectors that don't have the same length. So we can see that when we're doing scientific programming using vectors, a lot of errors can be caught actually before the actual program actually goes to runtime. Okay, so you see we can have conditions, we can have type check. These conditions actually run at compile time, that they actually enforce before the code actually runs. We can load vector data from files. So here we're loading it from, this is an iris data set we're loading from a file. And we can use F# operators to give us the length. So it's 150 elements in it. But that 150 is actually a type. It's not a regular value. And we can use, we can actually define functions that utilize this idea of doing static, the checks at compile time. So we can see here we have a function that checks whether the length of A is greater than B. So if I say here, so I can just put this here. So if I try to put in a vector of length 200 and a vector of length 100, it's actually going to complain because, sorry, this should be length 100 if I wanted to complain. Okay, so because our check condition is that the length of the first vector has to be more than the length of the second vector. And of course, this isn't true, so this is also be a type error. This is actually using, so they were actually using the type constraints inside the function. And of course, if I just change it to where it was before, so this will compile okay. Okay, so this is okay because the constraint is actually satisfied now. So we can move on to matrices. Now, the matrix, we can define a matrix of size, number of rows 4 and 200 columns. And again, we see that the matrix type actually has the dimensions of the matrix encoded as part of the type. So we can see here it's a floating point matrix that has with 4 rows, 200 columns. Okay, so that's actually, so the dimensions of the matrix are actually part of the type. And we can do the same sort of type checking we can do for matrix operations. So for example, here, the MINV, this is the inverse, the Sylvester matrix inverse operator. And of course, matrix inverses are only defined if the matrix is a square matrix. So I can calculate the inverse matrix for a square matrix. But if I try to, so let's try to calculate the inverse for a non-square matrix, like the one we created up there. Okay, so you see, so this code actually is not going to, this is, the type checker is going to complain because it's expecting the matrix dimensions basically to be equal to each other. And here they aren't equal. So this code will not compile. Okay, so the types of the matrix, they actually allow you to do a sort of type checking that depends on the dimensions of the matrix. Okay, so here again, we're creating two matrices. And in this case, we're just doing a matrix multiplication. So we can see here that this is a 9 by 20 matrix. And the second one is a 20 by 18. So these two matrices, they are conformable for matrix multiplication. So we can do matrix multiplication, and this is fine. We can use an operator to tell us what the size of the first dimension of this. So as we expect, the first dimension is of size 9, and the second dimension is of size 18. So that's the size of matrix you get if you multiply these two matrices. But if I try to multiply, so I'm going to try to multiply them in the reverse order. And of course, this is going to cause a type error because these two matrices, because they're not conformable. They're conformable the other way with the first matrix on the left hand side and this matrix on the right side as we have here, but they aren't conformable here. So again, this is a type error. This code will not compile. And of course, we can do matrix multiplication. We can do matrix and vector multiplication. So again, we're defining a matrix and a vector here. This matrix and this vector, they are conformable for multiplication. So this is fine. But let's say that I try to multiply this matrix by that vector of length 5. And of course, these two again, the multiplication between the vector and the matrix is not conformable. So this is a type error. So just a few other things that we can do. Well, we can actually slice into a matrix. So here we're slicing into our matrix. We want to get basically we want to get 4 values, 4 of the rows and 4 of the columns. So we can actually slice into this, and here of course we get, so if I try to get this value, okay, so this operator asks for the first dimension of the matrix, and of course that's what we wanted to slice into. Okay, so we can do things like we can append to a matrix using the same sort of operations that are checked. So here, for this very last statement, I'd like to append a column to our M99 matrix. So I can do this here, and that's fine. Okay, we actually get, so as expected, we do have basically the element is at 10, but if I try to append to a row of that does not fit that particular matrix. So see, again, that's a type error because the vector we're trying to append to the matrix, it doesn't have the correct dimension. So this will be a type error, and again, the code will not compile. So that's basically how Sylvester implements this idea of restricted or lightweight dependent typing for scientific computing. Okay, so I think my time is about up. You can check out the project at on GitHub. It's lsb/Sylvester, and you can also get me on Twitter. My Twitter handle is alstabihari. So thanks very much for having me, and take care. I'll see you around.